Okay, a lot of you requested intermolecular forces of attraction. So here we go. Um, we talked about this mostly during the bonding unit. Okay, so when we first started talking about bonding, we started talking about the bonding between one atom bonded to another atom. Okay, we said that that bond could be ionic, it could be covalent, it could be metallic. Those were the three big ones that we talked about. Um, intermolecular, it is intermolecular forces of attraction, mostly occur between covalent things, okay, between molecules. It's a molecule, it's covalent. So, this little picture that we have here with um, these lovely little molecules. This is a nice covalent solid. You can see that this is one molecule. This is another molecule. What holds them together? Why are they a solid? Okay. Why aren't they a liquid or a gas? What is holding them together? Those are your intermolecular forces of attraction. I am not talking about right here. I'm not talking about the bond between the two atoms. I'm talking about the bond between this molecule. I need to put my pen down. There we go. Between this molecule and this molecule. What holds them together? Those are what we refer to as IFAs. Okay? So, if you have really strong intermolecular forces of attraction, odds are it's going to be a solid. Okay? As they get weaker, or as you change the conditions, they become weaker and weaker and they move around. And then they become more of a, let's say this is more of a liquid. They don't really have the order anymore. They're moving around, they're moving past each other. Then, if your intermolecular forces are even weaker, we'll say that we have a gas. They're not held together very tightly. There's not a strong force here from molecule to molecule. Okay? The forces between those molecules. We talked about a number of different IFAs. Okay? We generally say that ionic things and metallic things and network covalent have really strong intermolecular forces. That's why they have high boiling points. That's why they have high melting points. It really gets a little bit more complicated when we talk about covalent, and that's why I say that covalent is what you're going to talk about for IFAs probably 90% of the time. All right. Melting points and boiling points are the two things affected by intermolecular forces. Okay? If you have a question that says, why is this melting point higher than this melting point? It has to do with IFAs. It has to do with intermolecular forces. You have more intermolecular forces of attraction, and I'm going to write that as IFAs. If you don't know that already, I don't know where you've been all year. If you have stronger intermolecular forces of attraction, those little particles are held together tighter. Okay? They're held together really tight. They're very much attracted to each other, like between there. Okay? So if I heat it, there's my flame, okay? As I add energy, it will break those bonds. But if there's stronger bonds, if there's stronger intermolecular forces, I have to put a lot more energy in. So the increase in intermolecular forces, the higher the intermolecular forces, the higher your melting point, okay? If your melting point is high, you're most likely going to be a solid. If your melting point is low, you're most likely going to be a gas, okay? The same goes for boiling point. If you have a lot, this arrow up means strong intermolecular forces of attraction. I'll write that. Strong. That means you should have a higher boiling point, okay? Something that is a liquid at room temperature, such as bromine, has stronger intermolecular forces than something that is a gas at room temperature, like fluorine. So bromine has greater IFAs than fluorine. For the only reason that bromine is a liquid and fluorine is a gas. Okay? On the regions, you'll be asked a lot of questions that are like, compare this to that. Compare the melting points and boiling point. Compare the melting points of these two substances, assuming that one has higher intermolecular forces. Or compare the intermolecular forces giving them boiling points and melting points. Just guess if you aren't sure, okay? It is a direct relationship here. As your intermolecular forces go up, your melting and boiling points go up. Vapor pressure is a little bit of a different situation. Vapor pressure is the pressure of the vapor. Seriously, it is that easy. Here's my liquid, okay? If I'm in a closed container, here's my little vapors up here running into the walls. Remember that collisions equal pressure. So as the vapor, as you have more and more vapor, as it evaporates easier and easier, your vapor pressure goes up. This is table H, okay? But how does a vapor pressure affect, or how does it change based on intermolecular forces? If you have stronger intermolecular forces, excuse me, you have a weaker vapor pressure. Why? Because they're held in here a lot stronger and they can't escape. Okay? They're held in the liquid. So as you have stronger IFAs, you have lower vapor pressure. VP is vapor pressure. Okay? Because it's held in the liquid and it can't become a vapor. Can't be a vapor, so there's very little pressure. So when you're looking at table H, ethanoic acid has the strongest intermolecular forces. Propanone has the weakest. Okay? That's how it affects vapor pressure. As intermolecular forces go up, melting points and boiling points go up, and vapor pressure goes down. These are the three new types of intermolecular forces that we talked about, that you need to know, okay? They are listed on this slide in order of strongest to weakest, okay? Now you have some additional knowledge that will help you understand this. Hydrogen bonding is a very special scenario. This is special. This only occurs when H is bonded to FON. Mr. Shiland always says hydrogen bonding is FON. F-O-N. Fluorine, that's not an N. There we go. Fluorine, oxygen, or nitrogen. Okay? If you have a hydrogen bonded to fluorine, a hydrogen bonded to oxygen, or a hydrogen bonded to nitrogen, and notice I'm filling all of them. Nitrogen makes 3 bonds. Let's put my lone pairs around. Okay? In these situations, you have hydrogen bonding. The hydrogen bond is not this. Okay? The hydrogen bond is the bond between this whole molecule and another whole molecule of it. Okay? So it would look like here's your oxygen and your hydrogen. Why does hydrogen bonding only occur with these 3 elements? Because they are tiny and they have an extremely high electronegativity. What that means is that your polarity here is really, oxygen is super strong and pulling those electrons. So oxygen has a partial negative charge, but it's like almost a complete negative charge. It's really, strong. And hydrogens, you know, from our acids and bases unit, are just a little baby proton. So they're very positive. So it makes the polarity here way greater than if it was just dipole-dipole. Makes the polarity way greater. So they can stick together a lot easier. And forgive my multiple colors here. Okay? This right here, I'm going to do it in green so you can see it. This is the hydrogen bond. It's not a physical bond. It's a force of attraction between molecule to molecule. Okay? Dipole-dipole is the polar molecules sticking together like magnets. Okay? So you've got maybe HCl. This is not hydrogen bonding because it's not bonded to F, O, or N. This is just dipole-dipole. Chlorine's a little bit negative, hydrogen's a little bit positive. So they stick together. They have stronger intermolecular forces than if they weren't polar. So these are just polar, but not the special case of hydrogen bonding. Okay? So polar molecules we've always said are like magnets. You've got your positive end and your negative end, and they're going to arrange themselves. They're going to spin around and arrange themselves so that they stick together. If something has dipole-dipole forces, it's going to have a slightly higher melting point and boiling point than if it didn't. If it has dipole-dipole forces, it's going to have a lower vapor pressure than if it didn't. Okay? Dispersion forces are your non-polar forces. We see these in things like methane, ethane, propane, butane, the alkane homologous series. Okay? CH4 is a gas. C2H6, which is ethane, is a gas. C3H8, which is propane in your gas grills, is a gas. But when you get to butane, which is C4H10, or pentane, which is C5H12, these become liquids. So based on this series, you can tell that the intermolecular forces are increasing. So as size increases, IFAs increase. They become more attractive as they get larger. Okay? This is nonpolar. How do they have these intermolecular forces if they're not polar? They don't have a positive end and a negative end. It's just the movement of electrons. These molecules are dynamic. Electrons do not stay static. They're not always in one place. They move around. Okay? Sometimes they're here, sometimes they're here. They move around. So when they're all kind of lined up, you can kind of induce some stickiness to them. Okay? As you get bigger, there's more places for that to happen. There's more places for those instantaneous, momentary sticky points. Okay? There's a lot more places for C5H12 to stick to another C5H12 than just a little baby methane molecule. Okay? The big thing you need to know about intermolecular forces, and I'm going to cut this very short because I don't want you sitting there too much longer. As intermolecular forces increase, boiling points increase, melting points increase, and vapor pressure decreases, because if it's held tighter in the liquid, you're going to have less of a vapor. Okay? Great.